Dr. French is the Alex Nassen Professor at the Department of Material Science and Engineering. He also holds secondary appointments in micromolecular science, biomedical engineering, and also physics department. He's also the director of the Crew Applied Data Science minor that is just opening. So with regards to big data, data science, this is a very important field that CASE is thinking of actually training the students in. He's also the director of the Solar Durability and Lifetime Extension SDLE Research Center. Prior to joining CASE, Dr. French was at DuPont Company and also at University of Pennsylvania. He received his BS from Cornell University and his PhD from MIT, both in material science. So the talk will be about the big data management that he had tackled about the analysis to drive photovoltaic reliability. Please welcome Dr. French.
So therefore, what I want to do as I talk to you about this is to tell you that set up the problem that we have in solar power, in PV, and this is a global challenge right now as PV is growing so much, and then look at how this is actually a big data analytics and high performance computing type problem. And so if you go and put a PV power plant in place either on your house or a gigawatt plant somewhere where you can put it on the ground, all of these basically are given a warranty such that their power will decrease about 1% a year over 25 years. And that's okay. No, there's not a problem here. It's, it's just the way that things go. But we don't really understand why that happens, and we don't know whether this is going to fail completely in, say, a few years, or whether it's going to go like this reliably. And so what we have is that we'd really like to understand more about what's going on here. And what we'd like to do is be able to break apart what's happening here and understand what are the rank order contributors to this loss of electric power generation over time. Okay, so that's a rather small technical question, but instead it's part of a bigger class of problems which I'm going to call high cost of failure devices. Okay, so there are these technologies where you put a lot of money in up front and then you just hope that they're going to last for 25 or 50 years, right? And so there's a big issue because we tend to do what's called reliability in engineering. People will be reliability engineers and they'll say, well, if you do this, it should last forever, don't worry. And it always follows with that don't worry kind of thing. Well, this is the first PV power plant built in the United States in the 80s after the crystalline silicon PV modules were developed. And it was built, it was 5 megawatts, it was very expensive, and it was said to have its power drop no more than 1% a year, so it should last for 25 years. Instead, after the first year, its power dropped 10%. After 5 years, it was half a power plant. And it was such an embarrassment technologically that they literally dug it out of the ground and threw it away to try and forget that this had happened. And of course, that kind of a fiasco couldn't really happen again, right? No one would ever invest tons of money and have a big fiasco. And then of course we can talk about the Boeing 787. So this is a plane which is one of the first ones ever to have allowed the use of lithium-ion batteries in an airplane. Airplanes are really important that they don't catch on fire. Lithium-ion batteries catch on fire. It's an odd combination there. And of course they spent, well, not only billions of dollars, but tens of billions of dollars developing the 787 with a statement from the reliability engineers that there would be one smoke event in 10 million flight hours. Okay? And instead, 4 planes caught fire out of 7 planes in the first 7 months. So again, sort of one of these fiascos. So there's something that we're really not connecting here between what actually happens in the real world and what we say happens when we do things in the lab. So the Department of Energy, because these have been rather big issues for quite some time, have had a series of reports about this, of basically saying, okay, these traditional reliability methods for long-lived technologies just aren't up to the job. How can we do things differently? Okay? And so what we really need is that all of that work has been done on, quote, accelerated tests. You cook something really hot in the lab, and if it lives through that, you should be okay. Right? It's that you should be okay again. What we really need is to come up with different ways to do this, and that's what we've been doing in our center. And so if you just looked at traditional reliability, it would be that you do an accelerated test. A standard one would be damp heat. All our electronics are subjected to 85 degrees centigrade, 85% humidity for 1,000 hours, and they should still work after that. And if they do, then you should be okay, right? And so this would be the one, and then maybe people have gotten up to having some physics of failure of how come it failed when it does. What we say is that for these long-lived real-world systems, it's not okay just to study things in the lab. We actually should be drawing upon all of this real-world data that's now available. Everything is generating data everywhere. Every product that is sold has the opportunity to supply information back to people telling us how it's behaving and what's happening. You can completely change the basis on which you do these studies. And so that's really what we do. We say, let's develop population-based studies, so epidemiology, okay, automated field reporting. Let's use data science. Let's crunch lots of numbers, make our numbers very easy to access and make use of. And then let's actually get this domain science-guided, statistically informed data analytics. And so that's really what we've been developing since I came to CASE. So there's a review paper, if you're interested, that we just put out last year that one can go find that's on this topic of degradation science. Let's make this degradation in the real world into an actual science. And so first I'm going to show you what we have to do for the informatics part of this, because this is almost the foundational aspect. It's actually one of the things that helped direct me that I was done with my time at DuPont and I should head to a university because of those 3 little papers from Google in 2005 and 6 about big table and MapReduce that basically have led to Hadoop. So I came here, and even as I was interviewing, I remember talking to people in IT and going, well, can we go do this kind of stuff here? You know, that's really important to me. And so by now what we've done is that we've actually gotten ourselves that we build these big Hadoop and HBase clusters in which we can take in real world data and lab experiments. Let's merge. We're not replacing the traditional ways, we're just adding an extra set of information. So do some informatics, curate and annotate our data, and then up here we can start building network models and looking out through all of the information that we have and get the outputs that we actually need to inform ourselves. Schematic diagrams are always very nice and neat. The reality is that, oh, if we need real world data on PV power plants, we have to go get some PV power plants and have them hand us the data. When I first got here, I thought I had my utility friends ready to give me their data, but everyone said, oh no, my data is proprietary, I can't give it to you, it's secret. And so therefore, we actually had to go build Sun Farm over on East 105th on West Campus. It's 122 power plants that got us started. We got all the way up to having 11. Actually, now there's 13 sites around the world. After the first one, all the other people paid for these 13 sites. We have other research places that have partnered up with us. So there's 5 here. MCCO, we do the Lakeview power plant. And then what we're going to do is we're going to take all the power data, weather data, and insolation data. It's flowing into our labs on a minute-by-minute basis, and we just basically curate, annotate, and ingest it into Hadoop and HBase. We built the first one in CSE IT. We now have moved up to HPC land, very nice environment. It's an unusual thing because that means that we're in my group, I'm a material scientist, we're doing a lot of computation. We build a lot of infrastructure. You know, I tell my students, okay, you should learn some sysadmin skills because otherwise how are you going to get anything done? That's a little different from the normal, say someone who just wants to run a big HPC job in VASP or something like that. So what we literally do is just have a host of computers that are taking care of data streams from around the world, preparing them, sticking them on our network drive, ingesting them into Hadoop, MapReduce, HBase, that's what we like, and then pulling them out for analytics or doing in-place analytics in Hadoop. The nice thing is that last summer we decided to move up and move go from Hadoop 1.12 to 2.5 and go up into HPC land. And at the same time, Obama, I love quoting Obama as a paper site, put out the National Strategic Computing Initiative, which said that high performance computing, so petaflop computing, needed to become common on the common basis with petabyte computing. right? So distributed computing and high performance computing should be brought together if we really want to get the advantages. And it just helped in a proposal we submitted that at Case we have a unified environment for this in HPC land. Works out very nicely. So we actually have, this is our own Energy Cradle Hadoop cluster right here, which then is just built into the normal HPC environment, so we can use any HPC node for grabbing some data on the fly, doing big computations, writing back our results, etc. It's really nice. Why do we like Hadoop and HBase so much? Because we will never have to refactor our database and rebuild our schema. Basically what we do is that we just take all of the information we put into HDFS, we give it a row key and a column key. This is a big bag of triples now. And then basically when we do a call with a cradle get command, it'll just assemble them like this, and it gives us back what looks like an SQL queryable table of data. So that means all the data that we've ever gotten, we can access whenever we need to, and we really have, scientifically, the version of the Google search box. We can just ask questions for data in data that we know exists, assembling it together however we want to on the fly. So let's go look at an example, and so this is Yang Hu's work in his thesis. This is our sun farm over here on campus, the first one. It was only after we started publishing papers of what we could learn from 122 power plants that all of a sudden we went to this case where we now are ingesting 2% of all of the PV power plants in the world. We are ingesting all of their data going back 17 years so that we actually have, now it's about 3.4 gigawatts of PV power plants that are going into our Hadoop cluster. 1.92%. It's actually now, it's about 7,400 PV plants at about 800 sites. And this is our epidemiological population for the real world behavior. And so what we do, here's a power plant, so M4JM. It's going to be interesting to know why we have such an obscure name here, but it's in a climate zone, which is BSK, arid, steep, cold area. And I'm going to compare it to another one that's in an arid, steep, same climate, but a hot condition. And it's exactly the same PV modules. I'll show you two of these just to try and get it down. Our data book tells us what data do we have accessible for this. We can just pull it all out as we need to. De-identification and anonymization. We actually learn a lot from our medical colleagues. Our PV power plants are not HIPAA. They don't have any rights. But actually our customers who give us all this data and who fund our research, if they're companies, very much want their data de-identified and anonymized. If you merge a ton of people's data together, that really helps hide things. You blur their latitude. And so we end up using script and basically making hashes and keys, and then we just simplify those down for human naming into a 7-character string. So we have about space for about 80 billion power plants or unique objects in our world. Works nicely. And then we do statistical analytics. So here's just a pairwise correlation plot, one of the first things we always do when we look at things. So AC power is related to the global horizontal irradiance, the brightness of the sunlight. Sun goes up, power goes up. Oh, but there's some glitches here we should look at. So have to do some data cleaning on this poll. This is actually 17 years of minute-by-minute data on a power plant that's been running that long. And we can just grab it and look at it. This is just one, but we actually would go through thousands of power plants to get statistically significant results. It's really quite different from having a student says, I've got an Excel spreadsheet on my computer and it's told me everything. So if we look at this right now, this is actually the month-by-month power production of this plant. You see some undulations here. And currently in science, what people do is they just fit a straight line to that data. They have so much data, and their best idea is let's fit a straight line. And they compare straight line slopes. Okay? Well, actually, if you look at this for a change point, it was the first 5 years, this thing hardly changed at all, and then it started degrading a bit. So that's interesting. That's the one in the cold environment. The exact same power plant, same age, same brand of modules, put into a hot climate, behaves like this. Scientifically, we have no understanding why this is. Should we model it by this big change point over here? Would it make more sense to go looking at all of these change points? This is where the power plant got better. It's currently unclear. We're uncovering all kinds of things from the real world that science hasn't even tried to address yet. What's going on with these things? So now though we want to go looking even at other types of information, and so this is a case where every PV power plant gives you an IV curve you could measure out of it, and it would tell you the behavior of the PV semiconductor cell. So that's a nice type of diagnostic. So not just a single power versus time, long, thin time series. We also have power plants where we get IV curve scans, one every 10 minutes. And that's a much more sensitive measure of what's going on. So we get these from the real world. Typically, they were only ever measured back in the lab. So this is actually a place where we can get direct comparison with more information out of that. But normally people would analyze their IV curve, a single one of these curves. And if they saw curves that looked anything like these are from real power plants, they would say, oh, that doesn't look like a simple IV curve. And they literally throw it away. They actually screened their data and would throw all of these away because they don't look simple, which is supposed to be a single bend. But the real world is doing this, and our science people were throwing away anything that didn't look like a single bend. So it's sort of like, okay, that's a very biased approach to things. Instead, what we have is from our sun farm here, take about 1 million of these on a single power plant over a year. Let's see how it's behaving. And then we want to analyze, well, what are these things telling us? What are the changes in slopes in these elbow points? Again, we don't know. This is almost more like discovery science. And so we go ahead and analyze these, and we can now, this case we analyzed 1 million IV curves in about 2 hours. Okay? Not a problem at all. You could do that on 1,000 of them. Not a problem. We have enough resources to do that. And now we can start classifying the behaviors by how many kicks, how many of those little knees are there, and what is the statistical relationship as we go looking at the life of this power plant, and how does it compare to all the other power plants in our suite that we're looking at. So this is really bringing new information to what we've got, and we can actually then start looking at, okay, these are the ones that were the green normal ones, yet in this case we had a large number of power plants that behave nothing like theory says they would. So we obviously need to advance our science to understand the real devices themselves. So that's another case of let's bring more computation once the data is accessible to us. We still want to get down to some real knowable mechanisms, those rank order contributors that I mentioned. And so that's what we do then with things where we're doing the experiments in the lab. And so here we'll take, this is a generic data block. We'll take a bunch of candidate materials, components, systems of any sort. Okay? And then we'll expose them outdoors and in the lab. Now we'll be able to cross-correlate quantitatively. We can do the performance that we actually cared about for this, and then we can do as many other measurements as we possibly can on those samples. And that can be point values like these things. They can be spectra like FTIR. They can be images that we can take, hyperspectral images. And again, this Hadoop and HBase approach that we do, we can just collect all the data that we want, annotate it a little bit, and make it accessible to us. So this data block allows one, and then we do stepwise exposures. That's what these little steps are. So now that data block, you sit down to do your thesis, you can basically ask any question of all the work you've been doing for the past few years to address what you care about in your science. So examples of that, here's a PV module. This is one that is being exposed to damp heat, that 8585, for 4,000 hours, and it's being cut apart to do extra measurements. And what happens is that for about 2,000 hours, it behaves just fine. And all of a sudden, there's a change point and the power production crashes. So it's being destroyed here, built by what built up in it during that phase. So again, it's one of these ones we don't really understand, and I can't just plot, oh, when this changed, this went up. Normally we scientifically say we're going to control all variables, and I'm only going to change one and watch the other. The real systems don't behave that way. And so what we instead get is that we can actually get mechanistic understandings with statistical behaviors from here was the power, here is EVA hydrolysis, here's polyester hydrolysis, and here is time. And we can actually put together a system where we understand the chemical mechanisms that led to the loss of power here. They can be both chemical mechanisms and then statistical jumps over them. So once we do this one, this is a simple network model. Okay? That's actually capturing the green here and the green here. We understand them. So now two more students, Nick Wheeler and Abdul Karim Gok. Nick is doing metallization corrosion. Abdul just graduated with his PET embrittlement thesis. And as we bring in a network model, we can integrate multiple models together, even from different studies, because we've captured the view of a whole system. And so in this case, for example, this is where we're taking images of the modules where we actually make them glow in the infrared by running power through them. We do image processing to line up all the cells, and then we'll quantitatively analyze the images of a cell and how it's slowly dying. That's 4 little cells right there. So we just automated image analytics. We want everything to be automated and streamlined. And then we do the same thing with spectra. So I'm just showing you some of the different ways we approach different things. So FTIR spectra, standardly, a professor would say, oh, you should use the 1096 peak, that represents this. We did in that paper I just showed you that there were 2 different peaks that, quote, both represent the same thing. If the student had chosen peak A, or the advisor, the result of the science would have been nothing was happening. If you had chosen peak B, all kinds of things were happening. So that little, I looked up in the literature and I'll use peak A, is a bias and a hazardous kind of thing to do. Instead, what we do is let's go do some statistical analysis on all the peaks there are and find correlation coefficients where we can see that as time went on, the system was actually responding. So again, you just need to be able to access your data and analyze it very nice and easily. And from these, you can then put together much more sophisticated network models to understand all the pathways that are activated in a real system. And so just sort of to wrap up, one, nothing actually gets done by a faculty member, and instead it's a whole bunch of good crew people. This picture is now out of date, and instead there's a bunch of new people who aren't showing there. There's also, so there are people are named over here. Then also all the people who fund our work, which is really important too. It's part of how we get this all done, and all the people that we partner with, both here at CASE and at other places. Thank you.
So again, if you have questions, feel free to move to the front. So I have one question. So you have a lot of big data, right? And sometimes you find something is amiss instead of the expectation. Do you always go back to the owner of the power plant and tell them, okay, what is going on with that difference?
We actually do. So we have a project that's starting right, I think May 1st it started. This is where we're doing the exact same thing for buildings. Instead of power plants, instead of producing power, they consume power. And we actually have customers now where we do energy analytics. And so this would be with Mohammed Hussein and with Ethan Pickering and Jack Mousseau, and Alexis Abramson is the other faculty member on this. And where we're studying power usage from smart meters of buildings. For example, one customer has got 500 buildings around the world, and they want to know how to allocate their annual energy saving budget in upgrades. And then we actually find for them a lot of times when their building management system is not working correctly, it's confused about what the time of day is or what the day of the year is, and we can see anomalous energy trends, and we just send them an email saying, you might need to go look at that building in Bangalore because it's not behaving like it should. And then they actually allocate, how much should we save from that one? And that's how they motivate their funding us, which is sort of nice. So there's actually there's both a feedback version, and then, so it depends on who the customer is. People making modules want to know how to make better modules. People who have power plants that look like they might die want to know what they could do to go run out and fix them to try and avoid that.
This is great. So what bottlenecks do you have, like, to make progress faster? Is it just humans trying to figure out what to do, or are you bottlenecked by not enough data, or computation, or network transfer?
So right now it's most probably this business, it's this business of getting good at building infrastructure. Having our 100 hundreds of computers running and doing the right thing. So right now we're doing lots for ETL and data ingestion and getting our data neat so we can find it and do that. We really want to get to the point where we have fully in place our analytics in Hadoop. So we haven't implemented that yet. We're taking an intermediate step. We'll do it on HPC nodes first with just a direct grab into memory. So it's mostly this one of balancing getting results that people care about so they'll fund us, letting students graduate and realizing when they shouldn't build infrastructure anymore, they need to do their science so they can graduate, and then getting the capabilities implemented. And you have to, that's a delicate balance there. It's sort of, you have to keep them all going.